Okay, so I'm going to do a couple more multiple regression videos. This is the one for today. And this is a standard example that I use. I have three different categories trying to predict a cost. Okay, MG, temp, ratio, whatever they stand for. So it's called multiple regression because I have, in this case, three variables trying to predict a fourth. Simple linear regression would just be where I have one variable. Okay, but this is multiple. And since it's, calm down here a little bit, since it's so many variables, I can't really picture this. This is in 4 dimensions, so we're not going there. But as far as doing the regression, I'm not going to have you worry about doing regression on the finding the output. I'm going to give you the output on the final. So I want you to worry about reading the output. And here is an Excel output. Well, StatCrunch is very similar. I mean, if you can read one, you can read the other. And what I want you to notice are a few things. R squared, 99.7. So R squared is the percent of the y values explained by the variation of the x values. So the closer that is to 1 or 100%, the better. Adjusted R squared is always going to be a little less. Adjusted R squared tells you what this does, plus it's also kind of giving you a measure of how efficient the model is. Are all these variables needed? Right here, the significance F is 6%. That's a little bit higher than I would like it to be. You'll see why in a second, but we'll roll with it. And the other things I have highlighted are what's important. So, first thing I would typically ask you for is the equation or the model. And you find that right here. These are the coefficients of the variables. So the word ratio is going to be a variable. I just made it capital so it's easier to see. But I would take this times ratio plus this times temp plus this times mg. I'm just going 2 decimal places. Minus, because it's negative here, the intercept. You have to remember to put that on. So that is my equation. That is predicting y. Y would represent cost. So the first thing you should do after getting the model is be prepared to do a prediction with it. So if I told you a number for ratio, a number for temp, and a number for mg, you'd plug those numbers in into the equation. It would spit out an answer, and that would be your approximation for what the cost would be at those settings. So how good of a model is this? Well, we would do global test. The global test is testing model adequacy, and you will have to do this on final. Hypotheses will look like this. Betas stand for the parameters. So beta ratio equal beta temp equal beta mg equals 0. So we're testing the null at these coefficients, like these numbers here, may as well be 0 against at least one's not 0. And if you fail to reject, that's bad. If you fail to reject, you're saying this may as well be true, implying all these parameters may as well just be 0, so your model will be no good. If I use 10%, I would reject. If I do the 10% level, that's my p-value. If I do the 10% level, I'm going to reject the null, saying at least one's not 0, and therefore the model is adequate. If I used 5%, I'd fail to reject, and the model would be adequate. We're going to go with the 10% option here, but I want you to don't get all hung up on the word adequate. If I always use this example in a face-to-face class. I'm going to hand them all shovels, and we're going to go out and dig a ditch. Now, can we do it with shovels? Yes, shovels are adequate, but is a backhoe better? Okay, and that's kind of what the word adequate means here too. Yeah, the model will work, but it might not be the best one. Individual parameter tests. So here, if I find the model's adequate, I would go on and do this test. And this test is looking at individual parameters. So I'm testing, is it 0 or is it not 0? We want to reject. If I reject, we're saying it's not 0 and it's important to the model. If I fail to reject, like I will on 2 of these, that'll tell me they're not important to the model, and I may as well just use one variable to do my prediction. So you find these p-values here, ratio, p-value. I just round them to the nearest percent, 16%, 18%, 3%. So 16% is way higher than 10. I would fail to reject. That means this value is not useful. Temp is also not useful because we failed to reject. I didn't write it here. I should, but I think I was out of room. I want you to write on the test all this information. This, p-value, failed to reject, not useful. Hypothesis, p-value, failed to reject, not useful. Here, I reject. That means it may as well, it is not 0 as far as we can tell. Therefore, it is useful. Rejecting implies that the variable is useful. Okay, and I just state that again. If I refit the model of just that one variable, you'll see my significance level here goes way down. And this is the same because it's just one variable. And that's my new model. You notice how it's simpler. Okay, it's a simpler model, but it's way more adequate. The smaller these p-values are, the more important they are to the model. If I come back up here, I can look at this and tell right away the best variable for prediction is this one here because the p-value is the smallest. Okay, so concludes model video 1.